Okay, my friend, so picture this. Though I presume you, mine ventilation engineer, have experienced this before, right?
Right.
Okay, picture this. Your mine has an exhaust race on top of which a main fan is installed. And every 5 or 6 months you have to change the fan because it failed. Their blades destroyed. And you wonder what happened. And you know that mine operations can't stop, don't you?
Yes, I do.
Having a main exhaust race out of service so frequently is unacceptable from the point of view of the well-being of the people inside the mine. So you do some auditing to that part of your mine ventilation system. You start assessing the fan installation, casing, blades, shaft, hub, but find nothing that could be directly involved in why every 6 months you have to repair the fan because its blades went off. At the same time, part of your personnel start inspecting the race looking for causes that may have increased its resistance. Sloughing, wall convergence, etc. But again, nothing wrong is found. But then you reconsider this issue and understand that measuring some data will give you some answers. So you start a psychrometric survey on the race. You measure barometric pressure and dry and wet bulb temperatures. The data you gather indicate that the air that enters the race is saturated. Saturated air and exhaust race tend to condense because as it goes up through the race, the barometric pressure decreases and thus the air temperature falls.
How does the water condense?
In really small droplets. So inside the race you will see this kind of fog formed at some portion of its length. The air continues to ascend inside the race and water continues to condense, resulting in more small droplets which, joined to the previous ones, create bigger droplets. So what you have inside your race is like a blanket of water that is going to create resistance to the flowing of air. Thus, the fan will try to struggle against that blanket of water by augmenting its fan pressure even to the stall zone in its operating curve. The stall zone is a region in which you don't want your fan to operate because it will operate unstably, oscillating between 2 fan pressures and 2 volume regimes. This movement will end up with your fan blades acting as cantilever beams, with their peak bending moment located now at their base, which will lead to their destruction. The phenomenon I just described is better known as water blanketing. This book here, this is the Spanish version of the Macpherson book, says in wet upcast shafts where condensation or water emissions result in airborne droplets, the air velocity should not lie between 7 to 12 meters per second. Water blanketing may occur in this range of velocities. The resulting variations in shaft resistance cause an oscillating load on main fans and can produce intermittent cascades of water falling to the shaft bottom. So, your velocity measurements inside that ventilation shaft indicate an air velocity of 8 meters per second. And then you're happy because you found the reason for your fans to be destroyed every 6 months. But just afterwards, you realize that you need to do something to elevate that velocity so it can be above 12 meters per second. You have different and even accompanying alternatives to do that. Installing a diffuser to the fan, change the fan blade settings. So by first performing the right measurements and then using low cost and simple actions, you can overcome the water blanketing problem. If you have any subject you want me to share with you, please just let me know that in the comment section. Do you want to get the book? Leave me a message here. So see you next time, Mine Ventilation Geeks, for more useful information.
Have a nice day.